Dear students, this class is going to deal about Newton's law. These laws are familiar to all of us, and these are the governing laws of physics. But still, let us explore. First, let us define or state the three laws of motion. First law states in an inertial frame of reference, an object either remains at rest or continues to move at constant velocity unless acted upon by a force. The second law states in an inertial frame of reference, the vector sum of the force F on an object is equal to the product of mass m of that object and acceleration a of the object. That is, F is equal to m into a. The famous third law states to every action there is an equal and opposite reaction. What are the implications of Newton's law? Laws are applied to objects which are idealized as single point masses because we focus only on the motion, so the size and shape of the objects are not considered. In the original form, Newton's law of motion are not adequate to characterize the motion of rigid body and deformable bodies. Newton's law holds good only with respect to a certain set of frames of reference which are called as Newtonian or inertial reference frame. That is why in the first, while stating the three laws, we use the word inertial reference frame. In the given interpretation, the mass, acceleration, momentum, and force are assumed to be externally defined quantities. Let us first consider Newton's second law. We know force is proportional to rate of change of momentum. Here P is the momentum, right? Whenever you have a proportionality sign, we will remove the proportionality sign by introducing a constant. So put a constant of proportionality K. So F is equal to K into dP by dt. The value of K depends on how we measure the force. We are going to choose the unit of force both in SI and CGS systems such that K is equal to 1. So your F becomes dP by dt. That is, the force is equal to rate of change of momentum and it is a quantitative measurement of force. Now consider a body moving with a mass m and velocity v. So we know the momentum is P is equal to mv. So you know already F is equal to d by dt of P. So instead of P you are putting mv here. So mass is a constant. So remove it out of the differentiation. So m into dv by dt. Now dv by dt is nothing but rate of change of velocity, which is nothing but acceleration. So F is equal to ma. So that is what your second law states. So F is equal to ma. The reverse is also possible. That is, from F is equal to ma, since Newton's law says F is equal to ma, we can also show that that is equal to rate of change of momentum. So starting from F is equal to ma, m is mass of the body and F is a force applied, and because of the force there is an acceleration which is a. We already know a is dv by dt where v is the velocity. Now instead of a substitute dv by dt. So what happens, you get m into dv by dt. Bring the m inside the differentiation, so you get d by dt of mv. Mv is nothing but the momentum, so F is equal to mv, sorry, dp by dt. Now assume that F is equal to 0, that is your left hand side is 0, which means dP by dt is equal to 0. Any constant that is differentiated will give 0, that is d by dt of a constant or differentiation of a constant is 0. Since we get dP by dt is 0, what happens is your velocity becomes a constant. So therefore, if the applied force is 0, the velocity is a constant, which is nothing but Newton's first law. Let me give you an example of Newton's law. When you are stepping out of a boat, The force that your foot exerts on the floor propels you forward. At the same time, an equal force on the boat is exerted in the opposite direction. When you compare the frictional force between boat and water and your shoes and the floor, the frictional force between shoes and floor is more. Therefore, what happens when you try to come out, the boat accelerates away from the dock, right? If you're going to forget this, what will happen is you will end up in water. Next, let us move on to motion of a rocket. First, let us see how a rocket propels. The force that propels a rocket is provided by combustion of the rocket fuel. Now, the fuel, when it is combined with oxygen, gases are produced, and there is a small nozzle through which the gases are directed. Okay, and each molecule of the fuel emerges out and accelerate away from the rocket. So Newton's third law required this acceleration and a corresponding acceleration in the opposite direction. Why? Because Newton's third law says for every action there is equal and opposite reaction. Okay, the combined acceleration of all the molecules of oxidized fuel as they emerge from the rocket nozzle create the thrust that accelerates and propels the rocket. Propels means rocket moving upward. Hot gases are exhausted through a nozzle of the rocket and they produce action force. So the reaction force acting in the opposite direction is called the thrust force, and this thrust force is responsible for rocket acceleration upwards. So this is a pictorial representation. You have the rocket movement. So this is the action, that is the fuel that is coming out. The reaction is the rocket propelling upwards. Okay, and we say exhaust flow pushed backward, engine pushed forward. So this is Newton's third law, rocket engine thrust. For every action there is equal and opposite reaction. Okay, now consider the initial mass of the rocket to be m and the initial velocity is v. Now we know mv, the momentum. So in a given time dt, the mass of the rocket decreases by dm, and therefore the velocity increases by dv, because p is m into v. So as m increases, v should decrease. We know from law of conservation of momentum, at the initial moment, the momentum of the system is mv. So we know now mass is reduced by dm. So you put instead of m into dm, and velocity is increased by dv. So put v plus dv. Let us call it as the initial momentum p1. Name the equation as 1. The momentum of the exhausted gas, right? We'll write it as p2 as dm, again the change in mass into the change in velocity. Here vu is the exhaust gas velocity with respect to the earth, so we are going to put that, and this is going to be in the opposite direction. Now we know adding p1 and p2 will give the total momentum. So p is the momentum mv, p1 plus p2 we are going to substitute. P1 already you know from equation 1, m minus dm into v plus dv, and now p2 is dm into v minus u. Now rearrange the equation. What we are doing is we are multiplying m into v, m into dv, dm into v, like that we are multiplying, and we are getting the fourth equation. Now this mv on the right side and mv on the left side gets cancelled. Your dm dv is very small quantity. Dm is change in mass, dv is change in velocity. When you multiply two small quantities, again it is going to be very small, so we are neglecting. The minus vdm and plus vdm gets cancelled. So you are left with mdv minus udm equal to 0, or mdv is equal to udm. So divide both sides by dv. So you get m dv by dt is equal to u dm by dt. Okay. Now m dv into dt is nothing but, now here the thrust force, because m into dv by dt is a acceleration. So t is equal to u into dm by dt. So this equation t is equal to u dm by dt is called differential equation of rocket motion. Thank you.